Hello friends, today's question. One end of a long metallic wire of length L is tied to the ceiling. The other end is tied to a massless spring of spring constant K. A mass M hangs freely from the free end of the spring. The area of cross section and the Young's modulus of the wire are A and Y respectively. If the mass is slightly pulled down and released, it will oscillate with a time period t, which is equal to. So in this case, we are given that there is a wire. Suppose this is a wire and its length is given as L and area of cross section is given as A and Young's modulus is given as Y. And to the other end of the this wire, a spring is connected, and to this free end of the spring, a body of mass M is connected. And it says that if this M mass is pulled down slightly, then it will be oscillating, and we have to find out the time period of that oscillation. In this case, as the wire is not, you can say it is having a Young's modulus of elasticity, or it is something that elastic, this wire is also going to behave like a spring. So we can draw a equivalent figure in which the wire can be represented as a spring. So this is the spring, which is a representation of the wire, and we have a spring connected, and this is mass M. Okay. And we say that the spring connected is having a spring constant of K, which is given, and the wire is having, let us suppose, a spring constant of K wire. So now we can say that the wire which is acting as a spring and the original spring, they are connected in series. And we have to find out the time period of the oscillation when this mass is slightly pulled down. Then we have to find out what will be the time period of the oscillation. So as now the wire is also acting as spring, so because of that there will be two restoring forces which will be acting on the mass. One will be due to the spring, whose spring constant is K, and another one will be due to the elongation of the wire, because now wire is also acting the spring. Therefore we can write that two restoring forces are acting on the mass M. First is due to spring, so this is our spring and this is our wire. Okay, here also this is our wire and this is our spring. First is due to spring, and second is due to elongation of metallic wire due to elongation of metallic wire which behaves like a spring, which behaves like a spring. So let us find out what will be the restoring force that will be because of the spring. So we can say that spring restoring force and spring restoring force, let us suppose, is given as Fs. The spring constant for the spring is given as K. So you can say spring constant for spring is equal to K. Then the restoring force Fs, then Fs will be equal to minus K into X, where X is the displacement. Okay. So this is the restoring force because of the spring. Now we can find out the wire restoring force. Wire restoring force. Okay. So the effective spring constant for the wire is given as K wire. So we can say spring constant for wire is taken as K wire. Therefore the wire restoring force, let us call that as F wire. So we can write that our F wire will be equal to minus K wire and multiply by X. And for wire, this X is the amount of elongation in the wire. So for the wire we take this X as delta L, where delta L is the amount of elongation under the force F wire. Therefore we can also write that this delta L will be equal to F wire multiplied by the total length L and area, and it is multiplied by the Young's modulus of elasticity Y. So we can write that our F wire is equal to minus K wire into delta L. So from here we can find out our delta L. So delta L is equal to F wire upon K wire. So substituting the value of delta L, so let us call this equation 1 and equation 2. So from equation 1 and 2, from equation 1 and 2 we get F wire oblique K wire is equal to F wire multiplied by L divided by area multiplied by Y, and these two terms cancel out. So from here we get the spring constant for the wire will be coming as AY multiplied by L. Now we know the spring constant of the spring, that is K, and we also know what is the spring constant for the wire, and these both are connected in series. So we can find out the total effective spring constant. Total effective spring constant, let us call that K effective, so we can say that wire and spring are connected in series, therefore K effective will be equal to K multiplied by K wire divided by K plus K wire. Now it's quite simple. We simply substitute value of K wire. So we get K effective is equal to K multiplied by AYL divided by K plus AYL, which comes equal to as KAY divided by KL plus AY. So we got the effective spring constant. Then the time period of oscillation, time period of oscillation, which is given as T is equal to 2 pi square root of M, that is mass which is connected to the spring, and divided by effective spring constant. We substitute the value, we get T 2 pi square root M, and we have KAY divided by KL plus AY, and now to a simple representation of the calculation, it will be coming as M multiplied by KL plus AY divided by KAY. So this is the time period of oscillation. This is time period of oscillation, and the options available to us, you can say that option number B is the correct option. Option B is correct. So this completes the question. Thank you.